Good day, everyone. This is our last video para sa ating midterms. So this is our last topic, oscillations. Madali lang ito, class. Mabilis lang itong topic na ito. Focus kayo sa ating terminologies and yung mga formulas nito. Okay, so let's start. So under sa ating oscillation, nandito ang ating periodic motion. Periodic motion, this is a repeating motion of an object in which the object continues to return to its given position after a fixed time interval. So we have here representation, ito. Familiar objects that exhibit a periodic motion includes a pendulum and a beach ball floating on the waves. So here, so ito yung ating mga representation. Sound waves, seismic waves, waves on stretched strings, and water waves are all produced by some source of oscillation. Next slide is yung motion of an object attached to a spring. So this system belongs to or exhibits simple harmonic motion. So this system that behaves in this way again are said to be exhibit simple harmonic motion. An object moves with simple harmonic motion whenever its acceleration is proportional to its position and is oppositely directed to the displacement from equilibrium. So balikan natin yung ating formula para sa force with respect sa spring. So F of S is equals to negative Kx. Yung K natin is yung ating stiffness ratio and then or stiffness value, and then yung X natin is yung stretch length ng spring from its original length. So other formula ng ating F or yung force is equals to ma or mass times acceleration. So, i-ano lang natin siya, equate lang natin siya. So, magiging ganito ang ating formula. Okay, ito siya. Kita nyo? Negative kx is equals to ma sub x. So, itong acceleration natin with respect sa x-axis. Kaya x ito siya. Representation lang itong x. Okay? So, negative stiffness value times itong stretch length is equals to mass times acceleration with respect to x-axis. Or pwede natin din i-represent ito, formula nito, kung ang hinahanap is yung acceleration natin. So equals to negative k over m times x, or negative stiffness value over mass times noong ating stretch length. Okay, next is the mathematical representation of harmonic motion. So ito yung ating formula. So itong harmonic motion natin, xt. So isang representation lang ito siya, ha. Yung kumbaga yung distance natin, yung stretch niya with respect sa period. Yung t kasi natin is period, okay? Is equals to a. Yung a natin is amplitude. And then a cos, open parentheses, yung ating omega, here, omega. Or yung ating angular frequency times yung t natin na yung t natin na period plus yung ating theta. Next, yung ating formula para sa ating angular frequency is equals to square root of k over m. So, or square root of stiffness value over the mass of the object. Okay, so yung A natin, again, is called the amplitude of the motion. It is simply the maximum value of the position on the particle in either the positive or negative x direction. And then yung ating omega is the constant or is called angular frequency. And its units or ang unit niya is rad per second. So again, be familiar sa formula ng ating harmonic motion. Again, this representation, isa lang ito. It is our harmonic motion, mathematical representation ng ating harmonic motion. So amplitude times cos, open parenthesis, yung ating angular frequency times period plus theta. Okay, next slide. Yung ating continuation. So yung t or yung period natin is equals to 2 pi over yung ating angular frequency. And then yung frequency natin, frequency f, is equals to 1 over yung ating period. Or another formula ng ating frequency is equals to i-apply lang natin kumbaga ito siya. So 1 over t nga. So lilipat lang siya. So magiging omega over 2 pi. So another formula ng ating omega or yung ating angular frequency is equals to 2 pi f or yung ating frequency, 2 pi frequency or 2 pi times frequency or is equals to 2 pi over t or yung ating 2 pi over period. So here, yung ating period t of the motion is the time interval required for the particle to go through one full cycle of its motion. And then the inverse of the period is called the frequency. Inverse, yung kabaliktaran niya lang, di ba? So yung ating frequency is 1 over t or 1 over the period. So inverse lang siya ng ating period. Whereas the period is the time interval per oscillation. The frequency represents the number of oscillations that the particle undergoes per unit time interval. The cycles per second or yung hertz natin. Hertz or ang kanyang symbol H, capital H, Z. So next, yung ating velocity. Velocity max is equals to angular frequency times amplitude. So ano lang natin, expand natin yung ating formula. So yung ating V sub max is equals to yung formula ng ating angular frequency. Yung unang formula niya is yung square root of K over M or stiffness over mass. And then times natin dito sa ating A na amplitude. So here is our formula. Next, in yung ating accelerations submax or maximum acceleration is equals to angular frequency squared A. So mangyayari yan, expand natin yung formula, magiging K over M A. Okay, here, balikan natin yung ating harmonic mathematical representation ng ating harmonic motion or harmonic motion formula. Xt is equals to the A cos angular frequency T plus theta. Yung velocity natin, derivation niya, dx over dt or negative angular frequency times amplitude, sine, open parenthesis, same here. So omega t plus theta. Next, yung ating acceleration, yung derivation niya. So d squared x over dt squared is equals to omega frequency, angular frequency squared, amplitude, cos, open parenthesis, yung ating omega t plus theta. So, be familiar with this formula. Magpabalik-balik lang ito siya with respect to our discussion na oscillation. So here, yung mga sample motion or cycle ng ating oscillation, yung kanyang period, full cycle. Next. So here, sample problem na tayo. Pero before tayo mag-proceed dito, meron lang tayong ito-play again ng mga videos para mas ma-visualize ninyo itong ating topic. Okay? So here is our first video. Okay, play na natin ang video.
Professor Dave here. Let's discuss simple harmonic motion.
He knows a lot about the science stuff. Professor Dave explains.
Sometimes when we examine the motion of an object, it will involve a single action, like a rock falling from a cliff down to the ground. This will probably just happen one time, after which the rock will remain at rest. But some motion is periodic, meaning repeated, like the motion of the pendulum on a grandfather clock, or the vibration of a spring. We will refer to this kind of motion as simple harmonic motion. Say we have a spring that is attached to some stationary surface, and on the other end of the spring there is a block of a particular mass. If we pull this block so as to expand the spring, and then we release the block, it will vibrate back and forth between more compressed and less compressed states. If we assume that the surface of motion is completely frictionless, then the elastic potential energy reaches a maximum when the spring is most or least compressed and the block is changing direction, while kinetic energy is at a maximum when the block is right in the middle and moving the fastest. If we were to graph the position of the block against time, it would display sinusoidal behavior, just like a trigonometric sine function, where the block continues to occupy the same positions over a particular period of time, which is why we call this periodic motion. X equals 0 at the equilibrium position of the block, where it sat before we pulled it, and assuming zero friction, the block will oscillate between positive x and negative x indefinitely. In reality, frictional forces will dampen the spring's activity, and it will eventually come to a stop. But for many systems, an ideal mass spring system will be a decent approximation for a real one. Of course, every spring is different. Some are loose, like a slinky, and some are stiff, like the spring that launches a pinball into play. This factor is represented by the spring constant K, which will be unique to a particular spring. The force that a spring can exert is equal to negative K times the displacement of the object it acts upon, and this relationship is called Hooke's law. The negative sign indicates that the force of the spring is always opposite the direction of the movement of the object. When the object compresses the spring, it will push out, and when the object stretches the spring, it will pull in. In both cases, the spring is attempting to move the object back to its equilibrium position, which is why the force applied by the spring can be called a restoring force. The units on a spring constant will be newtons per meter, so that when you multiply by some distance x, you get the force that must be applied to compress that spring that far. Let's also note that the elastic potential energy of a spring will be equal to 1/2 kx squared, where k is the spring constant and x is the distance it is stretched or compressed. If at equilibrium, the distance is 0, so it has 0 elastic potential energy, and the maximum elastic potential energy will occur at the maximum distance from this point on either side of the oscillation. This expression looks similar to the expression for kinetic energy, which is convenient since the two will interchange as the mass oscillates. A pendulum also displays periodic motion since it swings back and forth between the same two positions. Although this involves gravitational potential energy rather than elastic potential energy, and we will look at this behavior next. Let's check comprehension.
Okay, next video lang. Okay, class, this will be our last video for this topic. So i-play na natin ang video.
All right, so there's some terminology you got to get used to when dealing with simple harmonic oscillators, because people and books and teachers and professors are going to throw these terms around like crazy, and if you're not used to them, it could all sound like mathematical witchcraft. So the first term you got to know is that if you displace a mass from equilibrium, and why wouldn't you do that? That's how you get the thing to oscillate, by displacing it from equilibrium. The maximum magnitude of displacement, so this amount right here, whatever that distance is here, is called the amplitude. So we represent the amplitude with a capital A, and it's called the amplitude. And it's defined to be the maximum magnitude of displacement for that oscillator. So if this mass only ever makes it this far away, so from here to here, and I'm drawing arrows, but this is not a vector. It's the magnitude, right? The magnitude of the displacement. So it's the magnitude of a vector, so it's always positive. So we can draw that over here. If we want to, we could just say that this amplitude here, this would also be the amplitude, because we're just talking about the maximum magnitude of displacement. So it's going to get displaced equally on either side of the equilibrium position, and that maximum amount is called the amplitude. So in other words, if I pulled this mass back 20 centimeters, then that means 20 centimeters would be the amplitude, or if you wanted it in meters, it'd be 0.2 meters. And then that means when it shoots through the equilibrium position, it would also come over here and compress this spring by 20 centimeters on this side. So it's always equal on both sides. Now there's another term that you got to get used to, and that's the period. So the period is represented with a capital T. Why is the period represented with a capital T when there's no T in the word period? I'm not sure, but capital T is kind of like time, so T might stand for time. Maybe they thought that was a good idea, because what the period means is the time required for an entire cycle. So what does this mean, an entire cycle? What we mean is that you've got oscillations going on, and so this process is repeating itself. So in other words, if you start the mass over here, it's going to eventually make it over to this end over here, right? It goes over here, compresses the spring, then it's going to come back. The time it takes, it's a little hard to see, sorry, let me draw that up here. So the time it takes for it to go to here, and then come all the way back. After this happens, the whole thing just repeats. Now it's back here, the spring's gonna pull it back to the left, and then go to the right. And it's gonna pull it back to the left, push it back to the right. So this process is repeating itself. There's not something new happening. It's just the same process over and over. The time it takes to go through one entire cycle, i.e. the time it takes to reset, essentially. Once this entire system resets to the same position, that's the period. And so it's going to be the same, whether I count it as from this point back to that point, or if I imagine just starting my clock here, from this point, it's going to go over to here, then it's going to come back here. That would also be the period, because it's the time it took to reset. So the time it takes for this process to reset is what we call the period. It'll be given in seconds, and so for the sake of making this a little less abstract, let's say, for example, the period of this mass on a spring was 6 seconds. What would that mean? It would mean that it took 6 seconds for the mass to go from this point and then all the way back to that point, resetting itself. Now, this is getting kind of messy, and honestly, for that reason, people often draw what the simple harmonic oscillator looks like on a graph. It turns out to be particularly elegant and useful to represent these ideas on a graph, because look at, if you just drew what's happening, you'd be like, all right, the mass goes here, and then there, and then there, and then there. You're drawing all over yourself, and so that's kind of ugly looking. It's better to represent this on a graph. What would that look like? So let me get rid of this. It would look like this. You'd have a graph of the horizontal position, x. So what does that mean? That means this. So we're essentially graphing what this is. This is x, the horizontal position as a function of time. Now already you might be upset. You might be like, wait a minute, why did we stick the horizontal position on the vertical axis? Isn't that a dumb thing to do? Well, perhaps, but long ago, physicists decided, you know what? If time's involved, we're sticking that bad boy on the horizontal axis. This is just designated. This is just by default going to go on the horizontal axis. So if you have anything else you want to graph with it, that's got to go on the vertical axis. And so unfortunately, we're going to be graphing horizontal position on this vertical axis. What that means is that this equilibrium position, remember, this is the point where the net force, the restoring force, that net restoring force is 0. The only force on this mass in this case is the spring force, which is given by Hooke's law. And that means this equilibrium position is going to be the point where x equals 0. If I want my force to be 0, I better have x equals 0. So this equilibrium position right here, this line right here, let me give it a special color. This equilibrium position is essentially just this x equals 0 line, right? These two lines are representing the same thing. They represent x equals 0. And then if I go This way, if I pull this mass to the right, I'm essentially going up on this graph because I'm going toward positive horizontal positions. And if I go to the left, if I push this mass to the left, I'm essentially going down toward negative horizontal positions on this graph. So hopefully that doesn't freak you out too bad. Let me show you what this looks like. If we do displace this mass, let's say we pull it to the right, so like we had over here, right? We have this mass, we pull it to the right, and if we start at 20 centimeters from the equilibrium position and let go, what is that going to look like on this graph? Well, it started to the right. So if it starts to the right, I'm going to start way over here. At this point is my initial position. That means I'm going to start up here. I'm going to start up here at x equals 20 centimeters. So if we put that in meters, technically SI units, you should have meters for the default unit. So this would be 0.2 meters, and that's also the amplitude. So remember, this is the amplitude. So this distance here is the amplitude. And then what does the mass do? Well, it shoots back toward equilibrium. That's x equals 0. And then it oscillates. It goes through that point and comes back. So essentially what you're going to have on here goes toward equilibrium. So it looks like this, goes toward equilibrium, boom, hits equilibrium. That's when it's at x equals 0, passing through this point right here. Then it's going to come back down. It's eventually going to compress the spring and stop. That's when you're way over here and you've been stopped. The mass has been stopped by the spring. Then it's going to come back up in this process. It's going to repeat. It's going to go back through the equilibrium position and come back up, which by up means over here back to this initial point. That's one whole cycle. Look at that's gone through a whole cycle. Ugh, I kind of made this a little too high. Let me make that a little better. It should never go any higher than it started here. So it's going to look something like that, come back down, and this whole process repeats over and over and over. And if I was drawing this perfectly, it'd be perfectly smooth, but hopefully you get the idea. And this is great because now we can draw the variables we talked about earlier, like amplitude, because amplitude is the maximum magnitude of displacement from equilibrium. That would equal 0.2 meters. That's what we represented on this graph here. And we could also represent the period. Remember, the period was the time it takes to go through an entire cycle. So if our mass started here, to go through an entire cycle, it better get back to that point and have reset completely. So that would be to here. So on this graph, this is the period. So the time it took to do that is one whole period. That would be the period t, which, if we recall what we said earlier, we said that the period was 6 seconds. So if it really is 6 seconds, we could say that this here would be, if we count this is time t equals 0, this would be 6 seconds. This would be 3 seconds. That'd be half of a period or half of a cycle. This would be 9 seconds. This would be 12 seconds, which would be 2 whole periods. And that makes sense. It's gone through 2 whole cycles once it gets back to that point. Now notice, you didn't have to measure the period from peak to peak. You could have measured it from, sometimes people call these troughs or valleys. So you can measure it trough to trough or valley to valley. Look at 3 seconds to 9 seconds. That's a time of 6 seconds. It took 6 seconds to go from 3 seconds to 9 seconds. That's still one whole period. Or you can go from this point here, I guess this would be like 7.5 seconds, all the way to, what is this? 13.5 seconds. That would also be one whole period. Just make sure you don't do this. Sometimes people are like, oh, a period, eh? Repeat a whole cycle, eh? All right, I'm gonna go from this equilibrium position back to that equilibrium position. But that's not a whole cycle. Look at this point, the mass was going that way, and at this point, the mass was going that way. So you can't start your clock when the mass is going that way. Stop it when the mass is going the other way and say you've gone through a whole cycle, because that hasn't fully reset. If you're going to fully reset, you got to go from mass heading to the left through equilibrium all the way back to mass heading to the left through equilibrium. So you'd have to go from this equilibrium point all the way to that equilibrium point to have a full cycle. A cycle would look like this whole process right there. So recapping, the amplitude of a simple harmonic oscillator is the maximum magnitude of displacement from the equilibrium position. You can measure it that way, or you can measure it this way. You'll get the same amount. And the period is the time it takes for an oscillator to complete one entire cycle, which you can find on a graph by measuring the time it takes to go from peak to peak, from valley to valley, or from equilibrium position, skip an equilibrium position, and then get to the next equilibrium position. All right, so we saw that you could represent the motion of a simple harmonic oscillator on a horizontal position graph, and it looked...
So here, magdidiscuss na tayo ng kanyang mga sample problem. So first, we have the problem number 1. An object oscillates with simple harmonic motion along the x-axis. Its position varies with time according to the equation, yung kanina, yung x equals to a, tama ito, a cos angular frequency, t plus yung ating theta. So yung itong formula na to, may values na siya na ito, represented with this equation. So, x equals to 4 meters cos theta cos pi t plus pi over 4. So, ito yung ating omega. Ito yung ating pi. Ano pi? Ito yung ating... Wait lang. So, ito ang ating omega. And this whole part is yung ating ito yung ating amplitude. Okay? So, given na yung ating equation with its values or data. Where t is in seconds, okay? And the angles in the parent, these are in radians. So, A, first na tinatanong, determine the amplitude, frequency, and the period of motion. So, i-rewrite natin yung ating formula, okay? And then, rewrite na natin yung equation ng ating problem. So, here is the equation of our problem. So, write down lang yung ating amplitude, which is 4 meters. Okay? Yan. And then, yung ating omega or angular frequency is pi. And then, yung ating, ito siya naman is itong value na to. Okay? So, kunin natin ang amplitude. O, given na, nakuha na. Next is yung ating frequency. So, anong formula na ating frequency? It is angular frequency over 2 pi. So, yung ating angular frequency is nakuha na natin from this equation, di ba? So, i-substitute na natin dyan. So, we have pi over 2 pi or 1/2 hertz. Okay, yung frequency natin or 0.5 hertz. Itong Hz ang ating symbol sa ating hertz. The next, yung ating period. So, yung ating period is inverse lang siya ng ating frequency. So, ang ating period is equals to 1 over the frequency or 1 over 0.5, which is 2 seconds. Yung ating period is 2 seconds. So, nakuha natin ng ating frequency and then yung period of motion natin. Okay, next. Letter B. Wait lang. Okay, letter B. So, same pa din yung ating equation for this problem. So, where t is in second and the angles are in radians. So, letter B, calculate the velocity and acceleration of the object at any time. So, i-write down natin yung equation from our discussion kanina. Negative omega or negative angular frequency, amplitude, sine, open parentheses, angular frequency times t plus yung ating theta. So again, same lang sa kanina. Nakuha na natin yung ating A, itong amplitude natin, omega na, angular frequency. So from that, ipang-substitute lang natin. So meron tayong value ng ating velocity na negative 4 pi sine, open parentheses, pi t plus pi over 4, close parentheses. So ito yung ating equation para sa ating velocity. And then para sa ating acceleration from our previous a previous discussion, yung kanyang equation is 4 pi. Okay, sandali lang. Balikan natin yung ang kanyang formula. Parang nagulit ang aking